Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. I hope you had restful vacations. So we are going to continue today on Spark, and I'll show you more how it works and all the details. And yeah, that's pretty much the menu for today. But before we do that, I have a few questions for you. So here's the first one. So you saw that MapReduce works with key value pairs. Everything is a key value pair. The input is a collection of key value pairs. The intermediate output is a collection of key value pairs. And the final output is also a collection of key value pairs. But you know that not everything in the world is a key value pair or a collection of key value pairs, right? So what do we do? Do we use every block ID as the key and the blocks as values, and that's the inputs to MapReduce? Or do we hit the input with a hammer until it fits? Or is there a natural way to convert each input format into key value pairs? For example, in HBase, the row ID acts as a key and the row as a value. Or do we use each file name as a key and the content as a value? Giving you time to wake up a little bit. Right, so let's see. What you are saying. And indeed, there is a natural way. As we saw, for text, you typically actually map one line to a key value, with the content of the line being the value and the key is just an offset that you actually don't necessarily use in the query. File name as a key, content as a value. So theoretically, it would be possible, but that's not. That's a bit less common. Hitting the input with a hammer, well, some people actually tend to do these things, but that's not necessarily the most efficient way to use the technologies. And nobody said block ID, so yes, indeed, that one would be very inefficient because of the size of the blocks. Okay. So I have a series of questions for you. So here's another one. I introduced you before the holidays. MapReduce in its first version without Yarn, prior to Yarn. And then we introduced Yarn, which is used by the new version of MapReduce, but also by Spark. And so I'm asking, what did it solve? Why did we even bother to introduce Yarn and have a second version of MapReduce on top of Yarn? So is it that the map slots and the reduce slots were statically assigned, so they are often idle and that doesn't fully use cluster resources? Or is it that MapReduce splits span over two HDFS blocks and there's a massive drop in performance because data must be streamed from one data node over the network? Or is there a bottleneck on the job tracker, which is on the same node as the name node and the HMaster? Because the job tracker has to do both scheduling and monitoring, jack of all trades, master of none, or map slots and reduce slots are statically assigned before the job starts, and that leads to a suboptimal number of reducers. All right. So the majority identify the main reason indeed. So the most important one is that the job tracker does everything. It schedules things, it monitors things. That's too much for a single process. That is the main reason. And there's two other correct answers, is that indeed, before Yarn, in the first version, all the reduce slots were already created at the beginning, but you know they have nothing to do because they cannot start reducing until after all the map phase is complete, right? So that was a bit of a waste of resources. But with Yarn, you don't allocate them at the beginning, you only book them when you need them. So it's more efficient. And then in the meantime, other people can use the cluster or these parts of the cluster for something else. And then the last one is also true that the static assignment is also not optimal. Yeah. And the second one, technically, it's correct that it can span over two blocks, but it's not a massive drop in performance. It's just that you need a bit to read a bit remotely, but that wouldn't be massive. That's just little bits. Okay. Here's another one. What is an RDD? Do you remember? Resilience, distributed data set, recoverable distributed data set, recoverable dividable data set, resilient dividable data sets. Resilient distributed is the majority, and indeed, that is correct. Resilient, because if you lose them, it's no big deal, you just recompute them. So that's resilient. And distributed because, well, it's like in MapReduce, the collections of key-value pairs, it's just distributed and partitions all over the cluster. So that's why, and the others are just made up. And I think that's all I will ask for today. I also wanted to give this pointer, circling back on the discussion we had last week, that there are people who try to integrate LLMs with MapReduce. And this one, as I understand it, doesn't require a change in the architecture of the LLM. It's just a way to use MapReduce from outside. As I think they chunk the input collection, just like we chunk in MapReduce, and then they hierarchically trigger up all the answers. All right, so if anybody is interested in these things, then this is what you can take a look at. I'll put it in Zoom if anybody wants to see it. All right. So that brings us to where we were, which is pretty much here. The reason I'm going to that slide is that I didn't tell you what DAG means. Just say DAG, 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 because computer scientists say DAGs, but of course it's not obvious what DAG means. Does anybody know what DAG means? Yes? Exactly, it's a directed acyclic graph. That means that, so directed, as in D, means that they are arrows. So they have a direction. It goes from here to here, right? So these are arrows, so this is directed. Acyclic means you never come back to where you started if you follow the arrows. You see, it just flows through. You might have, if you didn't have the direction of the arrows, you would have cycle, if you would ignore the direction. But if you look at the direction, in fact, there are no cycles. So that is also known as a dependency graph. If anybody knows special relativity, then that would also correspond to causation or causal models. The interpretation is rather simple, is that since you have data computing from data computed from data, you cannot have a cycle because otherwise you would be computing data based on itself. And that, of course, we cannot do, right? So this is the reason. But the difference with MapReduce is that you might use the same intermediate data multiple times. So you might use this to compute something here, and also to compute something here, and also here, and also here. And then the other way around, you might have some data computed based on two sources, right? And everything here is an RDD. This is an RDD, this is an RDD, this is an RDD, this is an RDD, 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 right? Everything is an RDD. The RDDs are just the new collections of key-value pairs. just like in MapReduce, except that they do not need to be key values. They can be collections of whatever. An RDD is a collection of whatever. All right, so this is a DAG, a DAG, and that's the generic shape of a Spark job. Who is with me? Right, all right. So that I already showed you last time. RDD, this is what it means. It is partitioned just like the collections of key value pairs in MapReduce. And you can do three things with them. You can create them, you can transform them, and you can act on them. Right, and the actual action is what triggers all the computations, right? So you print it on your screen, or you write it to disk or to S3 or wherever you want, or you put it in a Python list locally, you download it and put it in a Python list. That's called materialization when you do that. All right, so again, this is just the illustration that I showed you that if you just create this DAG of RDDs, in fact, nothing will happen. Something will only happen at the moment that you pull the trigger here and actually ask for an action, right, on an RDD. And this will put the entire cluster into motion and going through the computation in parallel, right? We call that lazy evaluation. It means we don't start to compute anything until the user actually carries out an action and wants to see something on their screen. The implementation is in Scala. MapReduce was actually done in Java, HDFS also in Java. Spark was done in Scala, but you know that Java and Scala run on the same environment, in the same ecosystem, right? You might have heard, if you heard of Java, of the Java virtual machine, the JVM, so they all run on the same environment, and that means that you can also use Java with Spark just as efficiently. Python works too, but Python is a bit slower than the others because it requires a bit more interfaces between the Java Scala ecosystem and Python. And when you use Python with Spark, it's called PySpark, right? That's what it's called, PySpark. And in fact, if you install it with Python, that's pip install PySpark is the command. That's the name of the library. All right. And you can either write a full-blown application. If you love to write code, you can write something very complex, like if you want to build an LLM on top of that. Or you can use the shell, the interactive shell, and then you just type on the command line what you want. Here's an example of the interactive shell. That's something that you can actually do. You just need to run the Spark shell command in order to go there. So here I have a creation, the first of three ways to manipulate RDD. So I have a creation. What do? I have a Python list of just two strings. Of course, that's because it's only an example. In practice, it could be much larger, of course. But I have these two strings, hello world and hello there. I put them in a Python list, and parallelize turns the list into an RDD. Basically, puts the list on the cluster, and then you have an RDD with the same values you had on the list, but now it's on the cluster, right? Mathematically, it's the identity function. You didn't do anything. You just put it on the cluster, right? So then you create an RDD, you give it a name. So RDD1 is very common for samples to call them RDD1, RDD2, RDD3. SC means Spark context. It's just some object. When you activate the shell, it's already there, SC, you can just go ahead and use it. If you use Jupyter Notebooks, you might need to copy-paste from Stack Overflow a few lines of code that create SC for you, and then you can use it. All right, then we have a transformation. I put it in blue this time, so the creation in green, the transformation in blue. A transformation takes an RDD and creates another RDD. What do we do here? It's a flat map. Flat map basically maps every one of these elements that you have in your RDD. So in that case, there's two of them, hello world and hello there. And we need to say how we map them. Just like in MapReduce, we have the map function that we specify. And this is my map function. My map function splits with respect to space, right? That's a way in Python of just saying that there's a space here, so you cut it here, and there's a space here, so you cut it there. So that gives us 1 and 2 here, and 3 and 4 right here, right? So this is what value split does. And we call it flat map because then it flattens everything again, right? Once you're here, you just have a flat list of 4 tokens and you forgot where they came from, right? So it's flat. You no longer remember that these 2 were together and these 2 were together. In fact, flat map exactly corresponds to the map reduce map. This is the same thing. This is basically like a map reduce map. Okay, who is with me? Right. Lambda, don't be scared. That is just a way in some programming languages, it's called lambda calculus. It's a way to pass a function as a parameter, right? So you just say that's a function that takes an input called value, like x. If you do math, it's often called x, but here we call it value, and that associates value with value.split space. That basically cuts it in here. And lambda just says you make a function out of that, and then you pass that function to flat map, and then the RDD is mapped in this way, right? Now you might have noticed something else, is that I put these dashed lines over this, and I put these dashed lines around this RDD. I did that because, in fact, if you put this and press return, you will see that it instantly returns. There is absolutely no waiting whatsoever. The reason is nothing actually happens on the cluster. It just takes note that you would like the cluster to do that, but at that point, it doesn't do anything. So this is where at that point, nothing happens. This is the lazy evaluation. Now, if you want something to happen, then you need to actually trigger an action, like this count by value would be an action. And here, the moment you press enter, then you see your screen buzzing all over the place with all kinds of progress bars and so on. Like now, this is seriously happening. And then in the cluster, this will be calculated, this will be calculated, and this will be calculated. Count by value is just aggregating, counting how many times, how many words you have of each, right? So hello has 2, there has 1, and work has 1 out of these right here. And then in that case, that would be just a start to a local Python dictionary, right? That's just a local Python dictionary here, right? Everybody with me? All right, so that is just a simple example with one specific creation, one specific transformation, one specific action, very simple workflow. In practice, there are many, many more transformations, actions, and ways to create RDDs. And a program can be much more complex than that because this actually is very simple, right? If you draw the graph here, there's only 2 RDDs, right? So it's a very simple DAG. But in practice, that can be much more complex than that. And so from now on, we take it as a restaurant menu because unlike MapReduce that just has map and reduce, and there's nothing else, in Spark, you have a huge restaurant menu of transformations that you can use. It's dozens of them, maybe 100. By now, you typically find them either in books organized in lists of available transformations. You also find them on some websites. In fact, what is kind of strange is that the best list that there is in the Java doc of Spark, which is kind of strange because I would have expected there would be some documentation somewhere, like an official list. But yes, they are there, basically. So let me give some of them to you so that you see what they look like. So I'm going to start with a few transformations that just take an RDD, return an RDD, right? Plain and simple. And an RDD is just an RDD of values, an RDD of whatever you want. Can be integers, can be strings, can be dates, anything. So here's one. This is a transformation called filter. It outputs a subsequence of the input RDD, right? So you need to give it a function, with this lambda that I showed you earlier. You create your filtering function with lambda. This function should obviously return a Boolean, yes or no. And whenever the function returns a Boolean, the function is called on every one of the values in the RDD by Spark. If the function says yes, then you let it through. You let the value be in the output. If the function says no, then you exclude it and don't put it in the output. Right? This is called the filter transformation. This one is very simple. Right? Here's another one. This is called map. Now you put a function that maps a value to another value, and then it produces the output RDD having computed the value corresponding to every input value. Do not confuse it with flat map, because this map here outputs one value for every value, right? There is no flattening in there. So even though it's called map, be careful, that is not the MapReduce map. That is not the same one. The MapReduce map would be this one, where you have a map function that returns 0, 1, or more values for every input value, right? You remember that in MapReduce, the map function outputs 0, 1, or more pairs, right? So here, 0, 1, or more, that's a flat map, and you see everything is then flattened. You don't remember where these values came from, right? So map is like this, flat map is like that. Then we have another transformation that's called distinct. You know that some values might be the same in the input RDD. You might have a repetition of several times the same values. And distinct is a transformation that creates a smaller RDD that has eliminated the duplicates, right? So this is what it does here. Now, I would like to call your attention to the fact that this looks like a spaghetti, right? The arrows go in all directions. So you see something here is a bit different from the other ones. Here, it's not spaghetti as, in any way, right? You just have simple vertical lines. We will see that it has an impact on performance. And the reason is that this doesn't require shuffling, but this will require shuffling when you call this transformation. So this one is going to be a bit slower because of the spaghetti that you see in the relationships, right? So just have that in mind. Another one is called sample. Sample just rolls the die for every one of the values and keeps it or doesn't keep it. And you can specify the proportion or the probability thresholds for keeping a value. That has some applications in machine learning. For example, if you just want to take a sampled subset of the input. Is there a question?
Yeah, there's a question from the Zoom. The one student asks for, maybe it's for the last slide. So for distinct, we have 2 times the blue blocks in the reduced place. Why?
Oh, that's just because the details of the colors, maybe I didn't do them precise enough, but these are not the same. This is not the same. This is a lighter shade of blue as this one, right? This is really like the ones that are exactly the same go together, and this one is another one. Is this what you meant?
Yeah, maybe let's, yeah. He said, okay, yes.
Yeah? All right, so this is just, maybe I should slightly modify the color, but this is really another color here. It's not the same as here. Okay. So whenever it's the same, you just output it just once. Okay, thank you. So the sample with your, you take a certain proportion, but completely at random. Of course, when I say at random, it's not really random. It's what we call pseudo-random, meaning that you have ways to simulate randomness. But in fact, you can do it in a way that is reproducible, right? So this is the sort of techniques we have from cryptography to do that. And the way it works is that you put a seed into the randomness, and the seed is basically supposed to be taken randomly. Anyway, these are details that were outside of the material of the lecture. You can basically sample RDDs. Now there's many, many more transformations. Let's look at some other transformations that take 2 RDDs instead of just 1. There is a transformation that concatenates 2 RDDs. It's called union, which you could argue maybe applies to sets normally, but anyway, it's more like a concatenation, right? So you have 1 RDD on the left, 1 RDD on the right, and when you call union on these 2 RDDs, it creates a bigger RDD that concatenates the first 2, right? So that's another one. What else can you do? An intersection. So the intersection of 2 RDDs is going to return exactly those values that appear on both sides, both on the left and on the right, with duplicate elimination. So it also does the distinct thing, right? But it only puts those that are on both sides. So you see the yellow value is only on the right, so it gets excluded from the outputs. The red and black ones on the left are also not in the output, right? So this is intersection. You notice, again, this is spaghetti, right? goes all over the place. So there will be some shuffling in there in the physical layer. This doesn't have any spaghetti, right? The union is just straightforward. You will see there is an official name. They don't actually say spaghetti. There is a fancy name for that. All right. Here's another one that is called subtract. This one is outputting a subsequence of the left RDD, but excluding those that are on the right. So it's just a set subtraction, set in quotes, because the order is important. It's not actually a set, it's really a list, right? The order of values in an RDD is important. So this is subtract. And we have the Cartesian product of two RDDs. So you have the left RDD that I put vertically just because that's a Cartesian product, so I needed to organize it differently visually. So this is an RDD, this is another RDD. And the Cartesian product is outputting an RDD that has pairs. It's an RDD of pairs that has one coming from the left, one coming from the right, all possible combinations. So if you have 5 values here and 3 values there, you have 15 values. With great power comes great responsibility, because this is a best way to crash the cluster completely. Because imagine that you have an RDD with 1 billion values on the left, which is quite common to have actually, 1 billion values, and then another RDD with 1 billion values on the right. And if you compute the size of an RDD that is the Cartesian product, or a billion and a billion, that's basically 10 to the power of 9 squared. That's 10 to the power of 18. This is exabytes. That's quintillions, I think. 10 to the powers of 18. Sometimes I can make computing mistakes, but I think it's quintillions. This is going to crash the cluster. There is no way you are going to produce a quintillion values in a cluster today. That doesn't work. For this reason, in fact, by default, Spark, for your own safety, deactivates the Cartesian product. If you try to do it, you will get an error. And if you know what you are doing, and you know that it's actually small RDDs and it's all safe, then you can change the configuration and say, okay, I want to activate Cartesian products. Then you get a warning, like, be careful what you're doing. And then you can use the Cartesian product, okay? Just making you aware of that. All right, these are just a few of them. There's plenty of other transformations. I think there is an overview, a good overview in the O'Reilly book of Spark, which is given in the optional lecture materials. So they have tables that list all of the transformations available. And of course, in every version of Spark, they keep adding new and new transformations as we go. Okay, so these were transformations, meaning that they transform RDDs into RDDs. And now I'm going to give you some actions. So remember that the action is what actually triggers something. It prints something on your screen, it puts something on the local disk, it puts something on S3, on HDFS. The easiest one is collect. Collect is actually mathematically the identity function because it doesn't modify anything, but it moves the values physically. Collect downloads from the entire cluster all of the values of your RDD, downloads them to your laptop or to the machine on which you are calling the job, and puts it in a Python list, right? So even though it's the same values, on the top you have an RDD, on the bottom you have a Python list locally on your machine, or a Java list, right? So this is collect. Collect downloads. We also call materialize. It materializes the RDD locally as a Python list. Another one does a count. It just returns a single integer that is the number of values you have in your RDD. This one is safe. You cannot crash the cluster with this one, right? It's very efficient. Even if you have billions of them, it will just give you the count. Word of warning for collect. Obviously, if there's a billion values in your RDD, it's not a good idea to collect, right? You should collect if you know that you wrote your query in a way that this RDD is actually small. So you also have to keep in mind that it's not physically possible to collect a huge RDD that wouldn't fit on your laptop, right? So just a warning. But this one is safe. This one is count by value. That's the one I had in my example. That just returns a Python dictionary that says blue colon 12, yellow colon 4, green colon 6, right? It just counts how many values of each distinct kind there is, count by value. Now, what do you do if your RDD is way too big to be collected? Then you can collect just the first values, not all of them, but just the first n values. That is what the take action does. So if you say rdd.take 4, then you get the first 4 values locally as a Python list, right? So the difference with collect is that it's just a few. Top returns the largest 4. If it's integers, then it's just collecting the largest integers and so on and so on. That's another one. Take sample is similar to the sample transformation, except that this one downloads the samples to your laptop, right? Its take sample is giving you a Python list of these samples, right? So in that case, 4 of them. Then we have reduce. Now we are getting close to MapReduce, right, in terms of functionality, even though it's not exactly the MapReduce reduce. Reduce basically takes a binary operator, can be plus, can be multiplication, can be minimum, can be maximum. So anything that takes 2 values and returns 1 value, like the addition of 2 numbers, the multiplication of 2 numbers, and it applies it to the entire sequence. So it does this plus this plus this plus this plus this plus this plus this over the entire RDD. And the operator is supposed to be commutative and associative. And if it's commutative and associative, then the computation is very efficient to do that. And then it always works even if there's billions of values, because all you get on your laptop is the one value that is the result of applying that operation to all the values, okay? So this is called reduce. And yeah, so these are a few of the actions. There are many, many others, but these are the most common ones. Any questions so far? Right, on Zoom? All right, quick poll. Who thinks I'm going too fast? Who thinks I'm going too slow? Also not? All right, good, so I'm keeping the same speed. I always try to adjust, right? Because I neither want you to be lost nor to be bored. All right, so I'm done with the transformations and actions. Now I told you a difference with MapReduce is that MapReduce has pairs all over the place. Spark doesn't. Spark can have collections of whatever, RDDs of whatever, but this whatever can still be a pair. So it's still fine. In Spark, you can also have pairs if you want, RDDs of pairs. The Cartesian product was an example of that, producing an RDD of pairs. So let's say specifically the sort of transformations we have, if it turns out to have pairs. If you have an RDD of key values, then there's a transformation called key that just returns an RDD with the keys, right? This one is pretty simple. No spaghetti, by the way. This one doesn't have any spaghetti. Very straightforward. There's another one that's called values that takes an RDD of key values, but just return the values. Also no spaghetti in there. Another one is called reduce by key. In fact, this is the MapReduce, the one that would correspond to the MapReduce one. Because this one is going to look for all of the pairs that have the same key, like all the blue key, there's 1, 2, 3, 4 of them, and then applies a reduce function to the values that have the same key. That is MapReduce. That is the reduce of MapReduce, right? And so here, that outputs the this key value coming from here, 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 and here, this one coming from here, here, and here, and this one coming from here, here, and here. So I'm saying this is like the reduce of MapReduce almost, because in MapReduce, you remember that the reduce function can return 0, 1, or more key values. This one, I'm not sure if it can actually return more than 1. Might be limited to at most 1. So it's almost the same as the MapReduce reduce. Okay? But you see, with a flat map and reduce by key, you recover the MapReduce behavior, right? So this is why we say that Spark is a new generation of MapReduce. It can do what MapReduce can do, but more than that, right? All right. Here's another one called group. Oh, yes, is there a question?
Yeah, there's a question from the Zoom. There's one student asks, what will happen to the values of the keys in a reduced by key? And will they get added?
So the keys actually are unmodified. Let me explain why. These 4 key values, this one, this one, this one, and this one, they have the same key. They might have 4 different values, but they have the same key. Since they have the same key, it is that same key that you have here, right? So you don't need to do anything with the key because they're all the same, right? So you just take a copy of any of them, right? Does it make sense?
Let's wait. Yeah. Yeah, the follow-up question is, and what about the values? So
also, the values, you specify a reduce function, just like in MapReduce, you specify a reduce function. Here, you also specify a reduce function with your lambda syntax that I told you. Here, I gave plus as an example. If you have plus, then that would be this plus this plus this plus this gives you this value right here. But you, as the user, decides. You are the one who creates the function and who give the function to Spark. It does whatever you want it to do, right? So the function is your choice. Yeah.
Okay, thanks.
Yeah. All right, awesome. You see, it's a Lego game. It just provides you the skeleton, and you can just put whatever functions you want in there. Who played Legos? Some of you, right? It feels the same. It's really a Lego game. It feels exactly the same. Okay. Group by key is actually almost the same as reduce by key, except that it doesn't do anything to the values. It just puts them in a list or in an array, right? So that's all it does. So in that case, it would just collect all of the values that have the same key and put them in a list. So here you would have the key, the blue key, and then these 4 values are just a list of this, and this. Group by key, it is called. Of course, it only works if there are not too many values with the same key, right? Because if I give you an RDD that has 1 billion values with the same key, then this is going to break. If you try to do group by key, you're going to have a huge list of 1 billion values, and that probably is going to crash or slow down the cluster if you try to do that. So this is assuming that there are not too many values that have the same key. You can sort them too. It just sorts the key values by key, right? So sort by key. You can also map the values. It means that it just applies a map function, but just to the value, it preserves the keys and just modifies the values, right? And again, you specify whatever function you want that transform the values. Join takes 2 RDDs, 2 pair RDDs. Let's look at what's happening in here. If I join these 2 RDDs, it's going to try to look for pairs that have the same key, but on the 2 sides. For example, this one right here and this one have the same key, right? So it's combining them into this one. So the key, they have it common in there, and here you have the 2 values. It's basically a triplet, if you want, with the key, the value from the left, the value from the right. And it also has here the same key here, and produces this other combination, right? Then it has this one and this one that has the same key, so it also combines them. And here, probably these 2 have the same key also and combines them in here. If you remember joins from relational database systems, when you join tables, this does exactly the same thing, right? It just puts together the key values that have the same key on the left and on the right and puts them together. If there's multiple keys that are the same on the left or on the right, it just takes all combinations of them, right? That's what's happening with the blue key. Who is with me? Yes? Oh, a warning. So I don't think this one gives a warning because it's safer than the Cartesian product. Because the join, the size of a join, it's much less than that of a Cartesian product. Because here, what would be the Cartesian product? You have 5 times 4, you would have 20, right? But here you only have 4. So in many cases, I mean, if the typical way to use this transformation is, again, just like on the preceding one, that you don't have too many values with the same key. And if you don't have too many values with the same key, it's totally safe to use this one, right? If you want to crash, so if you want to, in spite of no warning, crash the cluster, just create an RDD with a billion key values that all have the same key and another RDD of a billion key values that also all have the same key, and then do the join, you will crash it because then you're going to have a quintillion values, right? But in practice, it's more often the case that the keys are distinct. And so this is why it's not deactivated by default, this one, I think. All right. Any other questions? All right. That's the joint transformation. I'm not even giving you all of them, right? Because there's a huge list of transformations that you can have, but just the common ones, a few important ones. Subtract by key is similar to the subtraction. It just outputs everything from the left, but excludes those who have a key that is also on the right. So the blue and orange, they get excluded from the left because they appear as keys on the right. So that's subtract by key. There is count by key, which is an action. And that here, it's obvious what it does, right? There's 6 blue keys, 1 green key, and 4 yellow key. And count by key gives you a Python dictionary. A Python dictionary is the same thing as a JSON object, right? The keys of the JSON object would be blue, yellow, blue, green, yellow. And if you see it in JSON, it's basically the object blue colon 6, comma, green colon 1, comma, yellow colon 4. That's your JSON object or Python dictionary. Okay. Lookup takes an RDD and it says, okay, give me the value associated with the orange key, right? And lookup is going to find it for you, right? It's a bit brute force because you are actually only looking for one, but it's like a needle in a haystack, right? But looking for a needle in a haystack is a walk in the park with Spark because you just do it in parallel, right? Imagine that you take your haystack, but you chunk the haystack into a billion, let's say a few thousand smaller haystacks, and then you look for the needle in parallel, right? So this is what lookup is going to do. So you can also do that, look up the value associated with a specific key. And yeah, that's pretty much it. That's what I wanted to show you. And there are many, 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 many other transformations and actions available. So typically when you use Spark, you just have the documentation open. By the way, you will have the documentation on exam day. We arrange that you have the Postgres documentation, the Spark documentation available. And you just look in the documentation for what you're looking for, right? And then write your query. Any questions so far? On Zoom? Also not? Yeah. All right, so now I'm basically done with the logical layer, right? So that's the how to use Spark, how to look up the transformations and actions, and then write a Spark job. Yes?
Yeah, suddenly a new question come, and the question is, what's the point of the transformation if we said that nothing happened?
It's just called lazy evaluation. In fact, if you use Spark, you will always have an action, right? When you use Spark, you always at the end trigger an action to get the result because you need to read the results of your query. How can I use a real life example? Imagine that you go to some shelter, like you to some service, and you request a document, but you never come back to actually get the document. You just ask for it and you don't come back. Imagine that they know you will not come back. Do you see that they don't need to actually create the document because they know you won't even come back and get it, right? So that's called lazy evaluation. Imagine that you create a Spark job, but you don't ask for the results ever. You don't say, download it to my screen. If you are the Spark cluster, then all you need to do is nothing because the user will not even know if they don't ask for the results. They won't see the difference if you actually computed something or did not compute something, right? So this is called lazy evaluation. And so this is the reason. But in practice, if you use Spark, you have to have an action. That's how it works, right?
Yeah. Yeah. And I think, yeah. Okay, it's
All
clear.
right,
Thanks.
awesome. It's just a matter of efficiency that you only compute what is necessary. All right, so now is actually the time for the break. And that's a very good place to have the break, because then after the break, I'm going to show you the physical layer of Spark. But as you will see, since you know how MapReduce actually works, there's not going to be so many surprises in the physical layer of Spark, as you will see. So thank you very much. Let's get some coffee, and I'll see you in 15 minutes at 9:15. Thank you.